Imagine stepping into the
Each
opening
squadron
days of
commander
America's
knows
entry
his
into
men.
World War II
And wise as a
discovering that
football
some of its
coach, he
most
lines up his
prized weapons
team,
were,
flight
quite
by
frankly,
flight.
a nightmare of engineering mishaps. To say that early war U.S. torpedoes had issues is to put it so gently that it almost feels dishonest. And yet,
And take it easy
isn't
now,
it
Kay, that
bewildering
releases
to
the
keep
whole
track of which
complex
model
machinery
failed in what
of
spectacular
another
way,
attack
and
in
how
the Battle
long
of Germany.
each flaw took to correct? Add to that
Roger.
the fact that U.S.
It's a belly
submarines,
tank job, so
aircraft,
get 'em
and
on.
surface ships
And the
all
same
relied
order
on
goes out
entirely different
to
torpedo
the ops
designs.
officers of the other
And you
squadrons.
suddenly find yourself navigating a maze of interrelated but distinct mechanical troubles. Each weapon demanded its own remedies, its own frustrating odyssey of fixes.
Briefing at 13:30 odd
Dear
job.
friends, if this
And
video
so the
has reached
details
you,
are sorted
it's not
out
by chance.
and boiled down into
Right
the
now,
field order by
click the
a
subscribe button and the notification
Within these
bell.
squadrons flew young
Write a
men.
number from 1 to 5 in the comments. I will personally respond to the first 50 comments, and make sure to watch the video until the end.
Joining the protective screen.
Now, before
Right,
you
we
rush
get a
to
rare
point out
glimpse
the
into the
wider
operations
arsenal,
of the
let me assure
56th
you,
and 4th.
yes, the U.S. Navy did indeed have additional torpedoes in service. Older models like the Mark X still lingered aboard aging S-class submarines, and later in the war, newcomers such as the electric Mark 18 would join the lineup, bringing, as you might imagine, a fresh batch of complications. But set those aside for the moment. Our story right now is focused on what the Navy
Fighter
considered
groups,
its
and even
latest
see
and
the
greatest
distinctive
in
twin-boomed
1941.
effect of the air war.
The Mark 13, the Mark
preserves a-
14, and the Mark 15. So let's journey through them one by one, starting, naturally, with the Mark 13. Picture this. The Mark 13 begins life not as a triumphant innovation, but as something of an oddity in the U.S. naval arsenal. The Navy's early attempt at aerial torpedo warfare hinged on the Mark 7, a 17.7-inch Bliss-Livet design issued just before World War I, originally intended for submarines and destroyers. Many navies took a similar path, repurposing ship-launched torpedoes for aircraft, but the Mark 7 quickly revealed how unsuitable it was for such a task. At first, the Navy tried lowering the torpedo to the water on a cable, an idea that sounds inventive until you imagine the tail snapping clean off the moment it touched the waves. So they switched to the more familiar method, dropping it from a mount slung beneath the aircraft. But while the Mark 7 was built to endure the brutal acceleration of being fired from a torpedo tube, it was far less capable when subjected to forces from the side. In other words, it tended to shatter when it hit the water. Worse still, its internal balance made it unstable in flight, so achieving the proper entry angle was more hope than science. This forced U.S. torpedo bomber crews into a terrifying routine, dragging their aircraft just above the water, less than a wingspan, and flying at barely above stall speed, simply to give the weapon a fighting chance of entering the sea correctly. Attempts to solve these issues often sabotaged one another. Reinforcing the torpedo's body to survive impact was largely nullified by a nose stabilizer meant to improve its airborne steadiness, a device that inadvertently concentrated stress in exactly the wrong place and overwhelmed the strengthening. A dedicated aerial torpedo design was proposed, but senior officers insisted it would be faster and cheaper to keep modifying the Mark 7. Spoiler, it wouldn't. By the late 1920s, the weapon could be dropped from the dizzying height of 65 feet and at speeds barely scraping into the triple digits. But as the 1920s gave way to the 1930s, it was undeniable. A new torpedo was essential. And so began the long, drawn-out birth of the Mark 13, a process devouring nearly the entire decade. While most nations stuck to long, relatively slender 18-inch torpedoes for aerial use, the Mark 13 went in a different direction entirely. It emerged as a near 221 to 2-inch wide brute, far broader than any contemporary surface or submarine-launched torpedo, yet significantly shorter. At just over 13 feet, it relied on its girth more than its length, a compromise that allowed aircraft of the era to lift it. Why such width? In part, to accommodate a larger warhead. The U.S. Navy harbored an almost obsessive desire to fit the most powerful explosive punch possible into its torpedoes. After nearly 8 years of development, the Mark 13 finally began reaching the fleet in 1938. In its initial service configuration, the Mark 13 weighed just under 2,000 pounds, stretched slightly under 131 feet, and carried roughly 400 pounds of TNT. Later variants would grow a bit in both length and weight, chiefly to pack in about 50% more explosive before eventually adopting the far more potent Torpex. Although introduced in 1938, production crept forward slowly. By the early 1940s, carrier-based torpedo squadrons possessed only 2 torpedoes per aircraft. Unlike the submarine launch designs, these stockpiles dwindled further because of training demands, with exercises consuming considerable numbers of torpedoes thanks to the high volume of aircraft dropping them. Unfortunately, many of the hard-won lessons from those exercises were either disregarded or acted upon far too slowly. And that leads us straight into the heart of the matter. The Mark 13's formidable list of problems, the most extensive of the 3 torpedoes we'll explore, astonishing as that may sound. Imagine a torpedo whose rudders seemed irresistibly drawn to the left, sending it arcing off like some confused mechanical whale instead of slicing forward in a straight line. On the rare occasions when it cooperated directionally, it might plunge into the depths as though dispatched on a mission to find Davy Jones himself, or, with equal enthusiasm, burst upward from the waves like a leaping dolphin. But all of that assumes the torpedo even reached the water intact. Despite being designed for higher speed drops, attempts to release it at the speeds outlined in the manual often tore the propellers clean off. Worse still, the airflow during descent could arm the detonator mid-flight. The result? A not uncommon spectacle, a Mark 13 detonating the instant it struck the sea. Imagine watching a weapon so stout and compact that once released, it twists through the air like a confused acrobat. That was the persistent curse of this torpedo. Its short, chunky frame caused it to wobble unpredictably in flight, striking the sea at all sorts of eccentric angles. And with every awkward splashdown, the impact sent shocks coursing through its internal control rods and gears, components reinforced for one expected axis of force, yet helpless against these new, unruly stresses. Every now and then, under conditions that felt as rare as a cosmic alignment, a carefully executed drop by an exceptionally skilled pilot would proceed without calamity. But those moments were the glittering exceptions, not the rule. One element, however, did generally function, provided it didn't arm itself a bit prematurely. This was the detonator, or the exploder, as the U.S. Navy preferred to call it. The Mark 13 relied on its own specially designed contact-only model, entirely separate from the notorious Mark 6 exploder installed in the Mark 14 and Mark 15 devices we will encounter soon enough. Still, even by mid-1943, during that brief lull when both sides in the Pacific momentarily stepped back from large carrier clashes, the torpedo's track record remained dismal. A study of 105 Mark 13 drops executed at a respectable operational pace revealed the grim statistics. Picture this. 36% of the torpedoes either refused to start their engines or shed their propellers altogether. The result in both cases was identical. They simply drifted nowhere. Another 20% plunged straight into the seabed, as though intent on attacking the ocean floor. Yet another 20% whirled off in tight, ridiculous circles. Meanwhile, 18% bobbed and dipped like passengers on a carnival ride, and 2% skimmed the surface as if trying their hand at surfing. In the end, fewer than 1/3 precisely 31% actually traveled toward their intended target. And if your sharp eye has noticed that these percentages exceed 100%, you're absolutely right. Many of these torpedoes displayed not just one failure, but several, a veritable collage of malfunctions. So what on earth could be done? Clearly, the Mark 13's woes couldn't be pinned on pilot error. With so many aviators, aircraft types, and tactical situations involved, no reasonable person could blame them all. The torpedo itself had become the prime suspect, and fixing it became an urgent priority. Yet the challenge was maddening. There were simply too many problems. Engineers tinkered with the torpedo's shape, making adjustments here and there, but the results were negligible. Soon it became painfully obvious that its greatest flaw lay in its utter instability in the air. Solve that, and many of the other issues might unravel themselves organically. Some proposed attaching small wings, turning the torpedo into a kind of primitive glide bomb. Technically feasible, yes, but the size, placement, and shape of the wings would vary depending on the aircraft carrying them, whether they were internally or externally mounted, and what speed or altitude the attack required. In other words, unless every pilot in every scenario followed an identical attack profile, an impossible expectation. This solution was doomed. The alternative was equally unappealing. Pilots would have to fly painfully low and unbearably slow, right through the eager sights of a target ship's anti-aircraft guns. Understandably, few aviators were excited by the idea. Thus, by the end of 1942, the Navy adopted a dual strategy: continue trying to rehabilitate the Mark 13 while simultaneously designing an entirely new air-dropped torpedo, should the original prove beyond salvation. But late in the following year, a breakthrough finally arrived. Minor adjustments to the propeller reduced the risk of them snapping off. Yet the real stroke of genius came with the addition of 3 new components: a plywood cylinder affixed to the nose, a box-shaped wooden stabilizer on the tail, and a metal shroud ring fitted around the propellers. Imagine the transformation. The 2 wooden attachments dramatically improved the torpedo's stability in flight, while increasing drag enough to slow it to a safer impact speed. When the torpedo struck the water, the plywood shattered and tore away, acting like sacrificial shock absorbers and sparing the Mark 13 from destructive force. The effect was so impressive that the torpedo could now be dropped at the speeds and altitudes originally intended, and then surpass them. It turned out the stabilizer created such a generous glide path that pilots could release the weapon from far higher and faster than any other aerial torpedo then in use. Even better, they could strike from greater standoff distances. This revolutionized survivability for torpedo crews and improved the torpedo's own performance. An Avenger, for instance, could now release a Mark 13 from just under 1,000 feet at full throttle, and newer, faster aircraft pushed these margins even further. The metal shroud ring, a permanent addition, solved most of the torpedo's underwater stability issues by smoothing water flow across its propellers and rudders. The price, a slight reduction in speed and range due to added drag, was trivial compared to the enormous gains. Almost overnight, nearly every Mark 13 began running straight and true, regardless of how high or fast it had been dropped. But you might be wondering, how long did this miracle take? The remarkable clustering of engineering breakthroughs meant that the Mark 13 endured roughly 2 years of being, at best, unreliable. Not until early 1944 did it truly come into its own. The urgency to fix it had become so great that replacement tail assemblies were produced specifically so they could be retrofitted onto existing torpedoes already aboard ships at sea, even as newly built units began incorporating the improvements from the outset. So how should we rate the Mark 13? Bad? Mediocre? Excellent. In the span of a few months, from late 1943 to early 1944, It transformed from a catastrophically flawed weapon, one whose shortcomings were rivaled only by the disastrously ineffective German aerial torpedoes, so poor that Germany abandoned them and purchased Italian models instead, into what by late 1944 had become arguably the finest aerial torpedo on Earth. Once aviators mastered the high-speed, high-altitude attack profile, which brings us to the Mark 14. Compared to the Mark 13's tortuous development, its backstory is refreshingly straightforward. The Mark 14 was created for the new generation of submarines entering U.S. service. Although the interwar Navy prized standardization, engineers understood that achieving the desired speed and explosive payload required a longer torpedo one too large to fit the tubes of older submarines. Thus, the Mark 14 was never meant to replace the Mark 10 or the handful of modified Mark 9 units used by R and S-class submarines, even though the submarines built for the Mark 14 would eventually replace those older boats in active service. To meet these needs, the specifications were set accordingly. Designed for submarine launch rather than aircraft deployment, the Mark 14 featured a 21-inch diameter, weighed roughly 3,000 pounds in its standard configuration, and stretched about 212 feet. Some sources say 21 feet, depending on which components one measures. It carried about 500 pounds of TNT as its warhead, could reach speeds of up to 46 knots, and boasted a maximum range of about 9,000 yards at lower speed settings. It was also outfitted with the new, highly sophisticated Mark 6 exploder, which promised both magnetic and contact detonation systems, along with improved depth control technology and several additional refinements. And what of its debut? Compared to the agonizingly long saga of the Mark 13, the Mark 14 all but glided into service designed, tested, and deployed within just a few years at the start of the 1930s. Now you might be wondering, what exactly went wrong with the Mark 14? After all, entire books have been devoted to its problems, shelves of them. Universities have produced theses by the dozen, and articles and videos, including my own, have tried to untangle the mess. But instead of keeping you captive for the next hour, retelling every single flaw in microscopic detail, let's step back and understand the big picture. The Mark 14's failures fell into three broad and maddening categories, each one cleverly hiding the next. Fix one, and only then would the next reveal itself like some unpleasant surprise waiting behind a door. These three categories were depth control, the magnetic detonation system, and the contact detonation system. And here's the infuriating part. When the torpedo ran too deep, no captain was shocked if it failed to explode. But once depth issues were corrected, and the weapon still didn't detonate, attention shifted to the magnetic influence mechanism. And once that was disabled, and the torpedo was finally set to a depth where it could strike a ship's hull directly, only then did commanders realize the awful truth. The contact detonator was just as unreliable. Let's start with depth control. This wasn't the result of one mistake, but several. The clearest culprit came from the torpedo's pre-war testing practices. Because warheads were becoming heavier and more powerful, and because nobody wanted to waste such an expensive weapon, test launches used inert torpedoes. These were configured to run beneath the target and then bob harmlessly to the surface, the warhead section replaced by empty space. Somewhere along the line, though, someone forgot to adjust for the weight difference. So the test torpedoes behaved perfectly, but when actual warheads were installed, the real Mark 14s plunged far below their intended depth, too deep even for their magnetic detonators to function. Compounding this was the nature of the test launches themselves. Many shots were fired at far lower accelerations than a submarine would produce, and at much shallower depths. Most tests came from barges, which meant the torpedoes never experienced the real-world conditions they would face when fired in combat. Then there were the calibration issues. In theory, each torpedo was supposed to be individually calibrated, with its unique characteristics: weight distribution, sensitivity, center of balance, internal equipment layout, recorded and sent along with it. Using these details, a submarine's torpedo officer could fine-tune the weapon before combat. But in practice, at least in some cases, generic calibration data replaced real measurements. The results bore little resemblance to how the actual torpedo behaved. And as if that weren't enough, the depth-sensing apparatus inside the torpedo had been relocated to accommodate new control systems. Unfortunately, its new position sat in a part of the casing where water flow reduced the surrounding pressure, meaning the torpedo believed it was at the correct depth only after diving far deeper than intended. Tank tests didn't uncover this problem because the torpedoes were essentially stationary, with no forward motion to create the pressure drop. Only when the weapon moved at full speed did the flaw appear. Understandably, it took time, too much time, to untangle this web of causes. Next came the magnetic influence component of the Mark VI exploder. This flaw wasn't unique to the U.S. Virtually every Navy that experimented with magnetic detonators early in World War II faced similar headaches. The root of the trouble? The Earth's magnetic field. Its strength and alignment change depending on latitude, shifting as you move between the poles and the equator. A detonator calibrated at Newport, the U.S. Navy's Torpedo Development Center, worked beautifully at that specific latitude. But closer to the equator, the magnetic field lines lie more horizontally and change more gradually. So a Mark XIV running beneath a ship at those latitudes might never encounter a strong enough gradient to trigger detonation at all. And if the torpedo was set too shallow, it could encounter the field too early, resulting in a premature explosion. Then, after the magnetic feature was finally disabled, crews uncovered the last unpleasant truth. The contact detonator was also defective. The device was designed so that the firing pin launched at a 90-degree angle to the impact direction. Combined with the much higher striking force produced by the faster Mark XIV, compared to the older Mark X, this flawed geometry proved disastrous. The guidance rods that held the pin warped under the sudden deceleration, causing the pin to jam, strike off-center, or land with insufficient force. The result? A dud or, at best, a feeble, low-order explosion. So how were these problems ultimately fixed? The depth control issues turned out to be the easiest. Once the underlying causes were understood, new settings and adjustments solved them one by one, and the sensors were simply moved to a place where they could feel the correct pressure. But repairing the Mark VI exploder was another matter entirely. Not because the solutions were impossible, but because the Bureau of Ordnance itself became an obstacle. Odd, isn't it? Especially given how quickly they responded to issues with the Mark XIII. But the Mark XIV faced several distinct challenges inside the Bureau. First, the Bureau seemed to operate in heavily isolated teams. Your experience with one group told you nothing about how another would treat you. Second, one of the officers who had originally developed the Mark VI and believed it flawless was now a flag officer in the Southwest Pacific. Positioned directly between the frontline submarines and the Bureau's engineers, he refused to accept that his creation could be anything less than perfect. Therefore, any failures had to be the fault of the submarine crews. His denial became a major roadblock and set a dangerous precedent for the Bureau's initial attitude toward the weapon. Third, the Mark VI had been wrapped in such intense secrecy that before the war, many Mark XIV torpedoes were actually equipped with a Mark V exploder, essentially a Mark VI stripped of its magnetic component. The manuals were classified so tightly that most sailors using the torpedo weren't even allowed to read the instructions. So when things went wrong, only a tiny handful of people actually understood how the system was supposed to work. And those few were separated from frontline crews by communication channels, tangled with personal agendas and professional pride. Picture, for a moment, that the United States was not alone in wrestling with the demons lurking inside magnetic influence detonators. Other great naval powers, the United Kingdom and Germany among them, found themselves staring at similar gremlins. The British, in their typically pragmatic fashion, simply stripped the troublesome magnetic devices out and reverted to contact fuses while their engineers labored to identify the flaw. The Germans, for their part, launched a series of corrective campaigns, some far less successful than they hoped, and even court-martialed several officers deemed responsible for the fiasco. Their efforts stumbled at first, but at least they reached the conclusion that the problem lay with the weapon, not with the crews, far sooner than the U.S. Bureau of Ordnance managed. Eventually, thanks largely to stubborn, often improvised field testing and the initiative of submarine crews operating at the sharp edge of the war, the magnetic influence component of the Mark VI exploder was simply switched off, put into limbo until someone could finally understand what on earth had gone wrong. That left the contact mechanism the last line of hope. Initially, the only emergency measure available was crude but necessary. Fire the torpedo at an angle that would soften the deceleration on impact, while further studies continued. These studies took on unusual, sometimes darkly comedic forms. Imagine warheads hoisted skyward, then dropped vertically onto steel plates, nearly always resulting in dud after dud. In one memorable incident, the only item damaged besides the torpedo's nose was some poor, unsuspecting equipment nearby, after the jammed Mark VI exploder popped free on impact and went sailing into surrounding gear and sheds like a rogue projectile. Inevitably, frustration among submarine crews boiled over. Tired of waiting for official fixes, they began devising their own solutions. And in the end, these grassroots innovations merged with the Bureau of Ordnance's more formal approaches. The final remedy involved reinforcing the guide rods, strengthening the firing spring, and lightening the firing pin. These adjustments at least made the contact detonation function of the Mark VI exploder reliable enough to trust in combat. And remember, this addressed only 3 of the major categories of failure. A handful of other issues lurked beneath the surface, problems that, in any other torpedo program, might have been called anything from irritating to serious. But for the Mark XIV, overshadowed by its towering list of catastrophes, these became minor footnotes in a much grander tragedy. So how long did the resurrection take? Despite the exasperatingly slow pace at which this arm of the Bureau of Ordnance worked, a combination of factors finally broke the logjam. Admiral King stepped in, Admiral Lockwood bypassed normal communication channels, and submarine crews doubled down on their increasingly daring improvised tests. The result: by mid-1943, slightly earlier than the Mark XIII achieved the same status, the Mark XIV had become broadly serviceable, at least in its contact detonation configuration. That represented a delay of a little over a year and a half between the emergence of the crisis and its general resolution. So where does that leave the Mark XIV? Bad? Average? Good? It began the war as arguably the least effective submarine-launched torpedo used by any nation in World War II. Yet it managed to claw its way back to relevance, even though, by the time its issues were finally corrected, it had been surpassed in speed, range, and destructive punch by several torpedoes employed by both Allied and Axis forces. It nonetheless proved to be a dependable, workable weapon, and it would continue to serve in various capacities well after the war ended. And now the stage shifts to the Mark XV. Conceived in the mid-1930s as the successor to the Mark XI and Mark XII surface-launched torpedoes, the Mark XV was the heavyweight of the trio we are examining today. it offered 3 selectable combinations of speed and range, and early planners even imagined it might one day serve as a universal torpedo across the entire fleet. But that dream dissolved quickly. To meet the range requirements for surface-launched weapons, the Mark 15 had to be too long to fit even the expanded tubes of the U.S. fleet submarines. And when designers tried to reconcile the needs of both surface ships and submarines, while also insisting on a very large warhead, they ended up with a torpedo far too heavy for the torpedo bombers of the 1930s and early 1940s to carry. Of the 3 torpedoes developed in the 1930s, the Mark 15 found itself placed on a relatively low production priority. Although it shared many components with the Mark 14, it was understood that aircraft and submarines would burn through their torpedo supplies far more quickly than destroyers, the primary surface torpedo platforms of the U.S. Navy. Moreover, many ships continued to use older Mark 8 torpedoes, and engineers extended the usefulness of the Mark 11 and Mark 12 through modifications. As a result, early trouble with the Mark 15 did not generate the same level of alarm as the nightmares emerging from the Mark 13 and Mark 14. In terms of specifications, the original Mark 15 weighed just under 3,500 pounds and carried a warhead of nearly 500 pounds of TNT. Like its cousins, it measured 21 inches in diameter, stretching almost 23 feet in length. Its top speed was roughly 45 knots at a range of 6,000 yards, dropping to a sluggish 26 knots if the crew needed it to travel out to 15,000 yards, though this slow-speed setting was seldom used. More typically, destroyer crews selected either the high-speed mode or the intermediate option. 10,000 yards at 331.2 knots. Introduced in 1935, the Mark 15 enjoyed more than half a decade before Pearl Harbor to filter gradually into the destroyer force of the U.S. Navy, as well as to take its place aboard the torpedo tubes of the Atlanta-class cruisers. But the Mark 15 had its own problems, many of them eerily similar to those haunting the Mark 14. Both weapons, after all, relied on the Mark 6 exploder. Fortunately, far fewer Mark 15 torpedoes were fired in the frantic early phases of the Pacific War compared to the avalanche of Mark 14 launches. And destroyer engagements tended to be wild, chaotic melees filled with gun flashes, evasive maneuvers, and deafening noise. In that environment, a torpedo that failed to detonate was usually chalked up as a simple miss, not a malfunction. Unlike submarine crews, no one topside was calmly noting depth settings or carefully tracking each torpedo's behavior amid the roar of combat. Some legitimate reasons underpinned this perception. The Mark 15 was often fired at medium speed, which increased the odds that the contact detonator would behave properly. The admiral responsible for developing the Mark 6 exploder operated within the Southwest Pacific Submarine Command, chain meaning that destroyer crews in the Central Pacific may never have heard his directives, much less felt compelled to obey them. This made disabling the magnetic influencer far easier. And because the Mark 15 was usually fired at maneuvering ships, its impact angle was often oblique rather than direct, reducing the force of deceleration, and thereby improving the chances that the contact mechanism would actually fire as intended. Now let's turn toward the destroyers, those sleek greyhounds of the fleet, and the torpedoes they carried. Unlike submarines, destroyers often set their weapons to run at depths almost guaranteed to strike a ship's hull directly. And because of that, even a torpedo running a bit too deep might still smash into the lower hull of an enemy vessel, or at least pass close enough for the magnetic influence feature to trigger. But this margin for error was limited. A torpedo that strayed slightly beneath its intended path might still serve its purpose. One that plunged far deeper. That weapon was gone, swallowed by the sea long before reaching its mark. And so depth-keeping remained a persistent trouble for the Mark 15, but not its only one. Recall that the Mark 15 initially sat low on the Navy's production priority list, Then imagine the sudden chaos when U.S. destroyers began loosing off their torpedoes in massive numbers during the Guadalcanal and Solomon Islands campaigns. Overnight, the Navy found itself staring at a dramatic shortage. The response? A frantic crash production program that swept in new, relatively inexperienced laborers. And with them came fresh headaches, inconsistent craftsmanship, and quality control failures that soon plagued the Mark 15. Then came the zinc problem. In an effort to conserve scarce cadmium, engineers plated the inside of the air flasks and related components with zinc instead. A clever idea in theory. In practice, a disaster. The zinc oxidized rapidly, shedding debris that clogged the torpedo's drive mechanisms. Imagine the frustration of watching a weapon built for speed and precision fall victim to something as simple as oxidized metal powder. By the time these issues were corrected, and in some cases retrofitted into the existing stockpile, the Mark 15 finally began behaving as its designers had always claimed it should. But now, fate delivered a final twist. Large enemy surface vessels, once prime targets, became increasingly scarce. Meanwhile, the threat from the air surged dramatically, with aircraft, and of course kamikazes, forcing many destroyers to remove some or all of their torpedo tubes in favor of heavier anti-aircraft armament. The result was almost ironic. After months spent scrambling to acquire enough Mark 15s, the Navy suddenly found itself with a surplus of them. So what solutions ultimately took hold? The fixes for depth keeping and the exploder mechanisms largely paralleled those for the Mark 14, since the problems were similar, sometimes identical. Thanks to this overlap, and despite the additional troubles mentioned earlier, the Mark 15 managed to achieve a reputation for being at least somewhat reliable by mid-1943. In fact, it reached that point a bit earlier than the other two torpedoes we've been discussing. As for the air flask issue, the solution involved either stripping out the affected assemblies and replacing them with cadmium-lined versions, or coating the zinc surfaces with an experimental epoxy resin. But how long did the full process of improving the Mark 15 actually take? That question is trickier than it sounds. Its reliability was never quite as catastrophic as that of the Mark 13 or Mark 14, yet it always lagged behind similar torpedoes used by other navies. After roughly a year to a year and a half, it reached a more dependable level, only to suffer a setback when the zinc problem emerged. Thus, in a sense, the Mark 15 was both the fastest and the slowest of the three to reach stable serviceability, depending on which stage of its development you examine. Was it a bad weapon? An average one? A good one? The answer, like the Mark 15's own history, wobbles. At times it dipped below average. At others, it rose above, slowly trending toward good as the war progressed, especially once it carried the formidable Torpex warhead. Even so, several destroyer-launched torpedoes on both sides outperformed it. But the Mark 15's demise had less to do with its inherent qualities and far more with the rapid decline of surface-launched anti-ship torpedoes in the U.S. Navy. Missiles would soon assume the anti-ship role, and specialized anti-submarine torpedoes would take over the space once reserved for the Mark 15's launchers. And with that, we arrive at a concise overview of the primary issues and their solutions for the U.S. Navy's frontline torpedoes at the dawn of World War II. When I return to my series on the U.S. Pacific Fleet submarine campaign, we'll dive even deeper into the trials and tribulations of the Mark 18. But that story awaits another day. Thanks for joining me. If you have thoughts or suggestions for another ship to explore, feel free to leave a comment below. And don't forget to share your dry dock questions on the pinned post.